All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Still a few people trickling in here. Okay. All right, so let's get started. Anything else I want to mention by way of housekeeping? So the first two lecture videos are already up. And I think I figured out the kinks with the video thing, but we'll see third time's the charm. So hopefully they'll be settled so that the videos will be up. There's a weird username here. Hold on. So I haven't been Zoom bombed yet, but knock on wood, I don't want it to ever happen. So if I see someone in the waiting room with a weird username, I'm like, please rename yourself before I let you in. Yeah. So I don't think I want to say anything. Hopefully everyone can get into web work. Hopefully everyone saw an email from Gradescope. Hopefully everyone gets emails from me. Videos should be sorted now. And I guess that's kind of it. We can just jump into it, I think. Something weird on my screen here. Okay, let's jump into it. All right, so hopefully everyone is seeing my screen. All right, so this was actually yesterday's lecture. I just want to do a quick recap of what we looked at. So the main star of yesterday's lecture, well, for the first third of yesterday's lecture was this guy. Very important formula that allows us to find the derivative of an inverse function. Later on, actually, I found the derivative of an inverse hyperbolic function, and I did this sort of maneuver. But hopefully you appreciate the steps I took was kind of what we would have done to derive that formula. So I didn't apply that formula directly, but it ended up being that formula, that 1 over thing here. So that also works, like this is a formula that works in general for finding the derivative of an inverse function. We use it to find the derivative of the inverse sine function and the inverse tangent function, also called the arcsine function, arctangent function, respectively. And we found a bunch of, using those formulas, we found a bunch of derivatives in various situations. I expect you to remember the derivative of the inverse sine inverse, as well as the derivative of tangent inverse. The other ones, not so much. We also looked at hyperbolic trig functions. Expect you to remember the important identities as well as their definitions in terms of exponentials. Well, this kind of falls in line with, what else coming in here? Falls in line with how things work in trig functions, so that shouldn't be too surprising. As well as I want you to remember these derivatives. I derived one of them for you, but not all of them, but I expect you to remember. We did a bunch of examples where we found derivatives in various situations, as well as integrals. Then we went on to the major part in our course. So dealing with integration and learning how to integrate various functions under various situations is going to be a huge chunk of our class. We're going to actually spend a while on this, learning various techniques and kind of drilling it so that we know how to deal with it. And the first new technique we learned was called integration by parts. Now, of course, that isn't to say that everything we knew before wasn't important, because in fact it is. In fact, we learned that whenever you see a random integral that you need to compute, you kind of go through a bunch of steps, which we call the art of integration, and you try to figure out, does a basic rule apply? Can I simplify it to look like a basic rule? Can I use substitution? That's all pretty much Calc 1 stuff. And then you start worrying about something more sophisticated like integration by parts. And ultimately, after I teach you all these techniques, I'm going to come back here, I'm going to summarize it, kind of give you a bird's eye view about the techniques, when to use them, when you can kind of guess that one might work versus the other, because integration isn't as straightforward as derivatives. It's not like the derivatives, oh, if I see a quotient, it's the quotient rule. If I see a product, it's the product rule. If I see a composite function, it's the chain rule. It's not actually that straightforward. So there is kind of an art to this, kind of some nuance here. But for now, we're learning a fourth technique, which is called integration by parts, and it is based on this formula. So last time I derived that formula for you, and we went through a very simple example of applying that formula. We also learned about liate, which is a mnemonic to help us know how to apply that formula in terms of choosing the parts. So it's called integration by parts because we look at the integral that we were given in terms of parts, and we have to identify what those parts are, and then we're going to use those parts to figure out these other parts to plug into this formula, and we choose the parts based on liate. So logs, inverse functions, algebraic functions, trig functions, and exponential functions. These are some classes of functions that we know about, and you choose in order from top to bottom. People higher in this list get to be u before people lower in this list. So if you have two different kinds of functions being multiplied, you can use this list to kind of determine who should be your u. It is worth mentioning, although I don't really want you to worry about it too much, that these two can be interchanged in terms of priorities. More people coming in here. So can be interchanged. In fact, another mnemonic is called lipit. So this is with logs, inverses, polynomials, exponentials, and trig functions. So the thing is, exponentials and trigs, they kind of have this property where they kind of revolve on themselves. So for example, the derivative of sine is cosine, and then the derivative of cosine, you get a sine again. And so you kind of see the same functions kind of coming up over and over again if you repeatedly differentiate or integrate them. The same thing happens with exponentials, right? You kind of see the functions repeating again. And that kind of property is why they're to the bottom of the list. It's also why you can kind of switch their order a little bit. But liate is how I learned it when I was, a little Jhevon. So that's what I'm going to tell you guys to do. But lipit is another one that you might have heard. It's essentially for the same reason. Helps us to know how to choose the parts in an integration by parts problem. So yeah, so we did that, and I left a bunch of things for you to try for next time. And that brings us to today's lecture, lecture 3. Okay, so last time we looked at the integration by parts formula. I asked you to try these for next time, and that's what we're going to do. So we're going to jump right in with part B. So, all right. So hopefully you guys actually tried this. So tell me what to do here. So first, I want to, because so we're doing integration by parts. So yeah, integration by parts is gonna happen. So, but I do want you to get into the mindset of you're going to be in a situation where you might not know that integration by parts is what you want to do. So I do want to reinforce that once you see an integral, you're going to think in a certain order. 1, does a basic rule apply? And if here, nah, right? No, a basic rule doesn't apply here. There's nothing like this in my table. Okay, so the next thing you think is, can I simplify to use a basic rule? And no, right? Like x squared ln x, what are you going to do to simplify this exactly? All right, there's no algebraic trick that's going to somehow meld them together or something. The third thing you're going to think, can a substitution work? Now, this one does take a little bit of experience to see, but you're always going to try it in your head. I'm going to save you some time and tell you that no, not really. But you would actually look to see if that would work. So you'd eyeball this and be like, okay, if I were to do substitution, what would I do? U equals x squared, then you get a du equals 2x. I don't have an extra 2x lying around. I don't have an extra factor of x. That's not really going to help. And then even if my dx is 2x, what am I going to do with that ln? That doesn't really mean anything. So if I say u equals x squared, ln x is going to be like some crazy exponential with maybe like a radical in it. It's like, no, that's not going to work out. If I make u equals ln x, the du is going to be 1 over x. Okay, so what am I going to do with the x squared? You're going to kind of quickly run through some things in your head and realize, substitution isn't really doing anything for me right now, right? But it's important that you actually think through these things, right? So is this a basic rule? Can I simplify to look like a basic rule? Is a substitution going to work? You kind of look at these things first, okay? And you're going to realize after a little bit of thought and with some experience, you'll realize this relatively quickly that nah, none of these 3 things are going to work. And that's where you think, you know, by parts. And this, like I said, the 4 is in quotation because by parts technically won't always be the 4th thing you think about. It depends on what you're looking at. So I just want to, you know, re-emphasize that. So now, once you realize that, okay, none of these first 3 things are going to work, let's try by parts. For whatever reason, you're going to have a reason to pick by parts. The first thing you're going to do is you're going to choose the parts. This means you're going to pick your u and you're going to pick your dv. Okay. So here, what is u and dv?
U should be the natural log of x.
Right, liate, right? So this guy here is an L. This guy here is an A. This guy here gets to be the U because of liate. So first thing you're going to say is like your U is going to be the ln x. Your dv is going to be that x squared dx. Okay, and those are the parts. Now, once you find the parts, you know you're eventually going to have to plug into this formula. So you need to find these other parts. So you have your u, you're going to need a du, and you have your dv, you're going to need the v to plug into the right side of this formula. So once you pick those parts, you're going to compute the other part. So this means your du is 1 over x dx. This also means your v is x cubed over 3. And so the second thing you're going to do is you're going to now plug into the formula. Okay. Or more specifically, the int by parts formula. Okay, so that's the second thing you're going to do. So you know that, you know, the integral of u dv is equal to u times v minus the integral of v du. So that's going to tell us that the integral of x squared ln x dx is going to be equal to u times v. So here's u is ln x, your v is x cubed over 3. Minus the integral of v du. So you're going to take that x cubed over 3, and you're going to multiply by 1 over x. And you're going to get x squared over 3. Okay, so that kind of is what's going to bring us here. Okay. So I see a random integral. I'm going to go through those 3 steps in my head. Always those 3 steps, always in that order, every single time. Is a basic rule can apply? Can I simplify to use a basic rule? Would a substitution work? You always think those 3 things first. If those don't work, then you do something harder, right? In this case, integration by parts is what we're picking. So now you know you're going to have to choose the parts. You're going to choose it according to Liate. Then you're going to plug into the formula. And now what you're going to realize is you can compute the original integral by computing the right side. Now the right side has another integral to it. Now, again, every single time you see an integral, you think the same thing. So once again, you're going to apply the art of integration here. Right? So once again, you're going to go through those steps. Okay, I have an integral I want to compute. Is it a basic rule? In this case, yeah, right? This is the power rule directly, right? I can factor out the 1/3 and I'd be left with x squared. Power rule directly applies. So that's the 3rd step. Compute the integral on the right using what we're calling the art of integration. So in this case, we have x squared ln x dx equals x cubed over 3 ln x minus. So this is going to give us x cubed over 9. Okay, so I'm kind of writing out everything. So on an exam, what you would write is what you see here in white ink, right? But I'm writing these other parts because I want you to know what was going through my head when I'm doing it. But essentially, those would be the steps. Okay. So that should give us a good recap of the last thing we spoke about yesterday. Any questions? Are we good? Can I move on? Okay, so essentially that's this guy. So that's the integral of x squared ln x. All right, let's move on to the next one. E to the x sine x. All right, so again, so we're encountering this integral in the wild. We want to compute it. So we're going to think, does a basic rule apply? No. Can I simplify this to look like a basic rule? No. Can a substitution work? What would a substitution be? U equals e to the x. It's not going to help. How is that going to help me with a sine x? U equals sine x. My du would be cosine x. How is that going to help me with an e to the x, right? Like what would I substitute? Nothing, right? So that's not going to work. So I go through all those 3 steps, doesn't work. So now I'm going to be like, all right, I see 2 different functions multiplying each other, you know, maybe an integration by parts is going to work. So now that I've done that, I'm going to know that I need to choose the parts. So I'm going to need to pick u and dv. What is u here?
e to the x.
Well, this is an E, this is a T. So we did say that E and T could be swapped. But let's actually just stick to the formula. It'll be less confusion. So e to the x could work, but I'd rather just stick to how the mnemonic that I gave you. So in the mnemonic, it's Liate, the T would come before the E. So let's make this sine of x. This guy would be e to the x dx. So my du is going to be what?
Cosine x.
Cosine of x dx. And my v is just going to be e to the x. So that means I'm going to plug into this formula. Let's call this I, so I don't have to copy the integral over again. I equals u times v minus the integral of v du. And we have that. So now we have to compute this integral. How are we going to do that?
A second integration by parts.
A second integration by parts. All right, so we're going to pick again a u and a dv. So u is going to be the cosine, dv is going to be the e to the x dx. Going to have du, that's going to be a minus sine x dx. The v is going to be e to the x, and I'm going to plug that in. So this is going to be equal to e to the x sine x minus, in parentheses, u times v minus, which now is going to become a plus because of the minus sign here, the integral of v du. So now we have another integral here. And what are we going to do with that? Yeah, Daniela?
Is this just going to keep going on forever?
Yeah, so we're going to spend forever working out this problem, just going in a loop, and just not do anything else on the test. Like, no. So, but yeah, it does look like we're going to go on forever, but there is actually a way out.
Is sine x supposed to be negative or?
Yeah, but there's a negative in the formula, right?
Okay.
So, yeah, there's a negative in the formula. So it's the negative of the negative, which made it positive. But yeah, it's like we ended up with the same guy we started with. Like, what do we do now?
Just move it to the left and you can solve for the original integral.
Yeah, that's the way out. You see, this is the original integral. It's like this here is the I. So it turns out now it's just an equation. So what I have is I equals e to the x sine x minus e to the x cosine x minus I, right? So it turns out it's algebra at this point. We just stopped the calculus because we got the guy that we started with. So now just move him to the other side because he's who we want to solve for. And so 2 times I is going to be this e to the x sine x minus e to the x cosine x. And so your I is going to be 1/2. And I could also factor out the e to the x. And we kind of know a plus c needs to be there, so I'll just put it because it's an indefinite integral. Yeah, so things are a little bit shaky there for a moment. So this is actually not something that can occur, so don't worry too much about it. Sometimes you can do integration by parts, and you go through a few iterations and you kind of end up with the guy that you started with. This particularly happens when you have things like trigs and exponentials interplaying with each other because they both kind of revolve on each other. So don't freak out. If you get the original guy, at that point, just treat it like an algebra equation and move the guy that you want to solve for to the other side. And yeah. So that is the integral of e to the x sine x. So if you actually differentiated this, you would get e to the x sine x. Left as an exercise for the reader. Okay. So that was an interesting example. Here is another interesting example. All right, what do we do here? Art of integration, right? So is there a basic rule? No. Can I simplify to a basic rule? No. Can I do a substitution? No. All right, so we know integration by parts is where we're going. What are the parts?
I repeatedly made the function of x u in multiple integrations by parts until I turned it into a constant.
Ah, okay. So u would be the x cubed. Your dv is e to the x dx by Liate. So your du is 3x squared. Your v is going to be e to the x. This is I. So you're going to plug that in. U times v minus the integral of v du. Right, and then you end up with this guy. So you're going to do another integration by parts. U equals 3x squared. Your du would be 6x dx. Your dv is going to be that e to the x dx. Your v is e to the x. So we're going to plug that in. So x cubed e to the x minus, in brackets, u times v minus the integral of v du. And we have a third integral. Coming in. So we're going to do the same thing. It's the same kind of guy. So, okay, u equals 6x. Hopefully this is the last time. D is going to be 6dx. dv is going to be e to the x dx. V is going to be e to the x. I'm going to plug that in. U times v minus the integral of v du. And now this one is something that we can just use a basic rule for. So we would end up with x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. And I mean, you could factor out an e to the x or whatever. Or the basic rule comes in here. So yeah, we repeatedly did integration by parts, right? You have to kind of break this down like 3 times. And then the 3rd time we finished it. So you should get something like that as the answer. And yeah, you differentiate that, which I probably factor out the e to the x before differentiating and just use like the product rule. You will get ultimately x cubed e to the x. Any questions on this one? All right, moving on to the next one. So this is actually similar to the first one, but this is like x to the 5th. So what do we do here?
U is x to the 5th.
So you're just going to dive in and we're just going to do what we did before. Right. So, I mean, x to the 5th means what? We're going to do five integration by parts, right? Yeah, I say nah, not doing that. Got to be a better way. I'm not gonna sit here and do 5 integration by parts. Are you kidding me? What is wrong with you, Jhevon? Why would you even give us a problem like this? This is so, got to be a better way. There is, so luckily for you. So this was just my excuse to introduce another technique, which is kind of like a half technique. So it's still integration by parts, but it turns out we can actually streamline the process of integration by parts. We can actually put it in a frame that makes it actually easy to go through. Now, generally speaking, if you just have like a small problem like this guy, where essentially after applying integration by parts, it's really a one-liner, I wouldn't really worry about anything more fancy than that. But it turns out if you encounter something like this, where it's like, man, I got to do integration by parts like 15 times, like you probably don't want to spend your time on that. And it turns out there's a way to streamline integration by parts. So it's called tabular integration. So let me introduce you to tabular integration. So I'm going to show you how this is going to work. So here's how it's going to work. So I'm going to give you the algorithm, and then I'm going to do some examples. Because me just writing out the algorithm might be a little bit confusing, but in hindsight, it'll make more sense after you see an example, and then you can use the algorithm as a reference. So essentially, it's called tabular integration because you're going to kind of set up a table. You're going to kind of set up a table where one column corresponds to the U's that you're going to get repeatedly. One column is going to correspond to the DVs that you're going to get repeatedly. And you're going to line these guys up in a nice table, and you're going to use that table to your advantage. Because at the end of the day, you'll realize that you keep multiplying these guys. You multiply a U by a V, and then you multiply a dv by a u. So it turns out there's a way that you can multiply across these columns of the table that's going to allow you to populate what the formula that you would get after doing a bunch of repeated integration by parts. So here is how it would work. So suppose you have an integral, it's like f of x times g of x, where you want to use by parts with the u equals f of x and the g of x dx, the v equals that guy, not the v, the dv equals the g of x. Right? So you have an integral that you're like, okay, integration by parts is going to work here. So I'm going to pick the big function f to be the u and the other function to be the g, right? You can actually set this integral up, and I'm going to need a lot more space here to talk about this. You can actually set this integral up in a table. So here's how you would do it. So you're going to have this integral here. Where this guy is going to be your u, and this guy is going to be your dv. So what you're actually going to do is you're going to draw a table below that. So create one column here, and you're going to have a bunch of rows right under that integral. Okay. Now, in the u column, repeated differentiate this column. And in the v column, you're going to repeatedly integrate that column. And you're going to do this repeatedly, but there's going to come a point where you actually stop the process, right? So you're going to do this for some amount of time. And I'm going to tell you exactly how many times to do it. But that's what you're going to do. So you're going to find f prime, then you're going to find f double prime, then you're going to find f triple prime, f to the fourth derivative, right? And you're going to keep going until you do it n times, f to the nth derivative. Right? So in the u column, you just keep repeatedly differentiate because you're always going to pick the u to be this kind of function that was on the left. And you're always going to pick the dv to be the kind of function that's on the right. So this one, let's use g1 for the first integral, and then g2 for the second, and then g3, g4, going all the way down to gn, where gi is the ith integral. Okay. So you line up the integral, so your u is on the left, your dv is on the right. You repeatedly differentiate the left column, repeatedly integrate the right column. You will do this n times, and I'm going to tell you how many times, how to pick what n is. And here's how you're going to do it. You're going to start multiplying along the diagonal. So you're going to take this times that. You'll notice that that is going to be a u times v, right? Because if the g was a dv, when you integrate it, it's going to be a v now, right? And then you would pick that guy as the new dv, and then the g2 would be the v afterwards, and then you pick that guy as the new dv, and then the g3 would be the, And so this is the process of you multiplying the u times the v. Of course, that takes a plus sign. This is going to be the new u and the v. That'll take a minus sign. And why that takes a minus sign is because of something that we saw earlier, right? Where this plus sign came from. It's because we're taking a minus of a minus. When you plug it into the formula, you have these nested parentheses, but there's a negative sign that's always changing the sign of what's inside the parentheses. So that's going to be a plus, that's going to be a minus, this is going to be a plus, this is going to be a minus, and you're going to actually continue this process. Now there's going to come a point where you're going to get to the bottom of this, and we don't know what sign that's going to be. So this is going to be a plus or minus. And then what you're going to do is you're going to multiply across here. And that is when you finish everything, that's like you multiplying your v times the du. And this is going to, of course, be the opposite sign. So it turns out you can start writing out all these products, and the last one is going to be the final integral that should be the easiest one to do. So you end up with this sort of scenario. You end up with f of x, g of x, dx equals, you're going to have like the f times the g1, right? Then minus the f prime times the g2 plus the f double prime times the g3 minus dot, 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 right? So that's what these guys that we're multiplying here. Eventually, you're going to get to a plus or minus. It depends on how long this process lasts, but ultimately, you're going to get an integral of the f n g n dx. And so this here is a generalized version of integration by parts, right? But you always set it up with this table, right? You don't have to memorize that formula, but essentially this is how you piece everything together. Okay, so let's actually do an example. And you're going to see that it's a lot easier to actually think about it this way. So let's go back to x to the fifth e to the x dx. Okay. So what you can do is immediately below this integral. So you know it's going to be integration by parts, and you can see that it's going to be repeated integration by parts, because it's going to take you a while to break down that x to the fifth until it becomes a constant, and the e to the x is just going to be revolving. So yeah, we're going to go through a few of them. What I can do right here is just draw a table right under this integral. Oh, I should probably tell you when to stop. Yeah, that's what I forgot to tell you. Because I just tell you you're doing this n times. So how do you know what is n? So let's actually deal with that. When to stop and terminate the table. Stop when one of the following occurs. So 1, the derivative column eventually will hit 0. Now, obviously, that's going to happen if you have a polynomial, right? Like the x to the third is going to become an x to the squared, and that's going to become an x, and the x is going to become a constant, right? And then the derivative of a constant is going to give you 0. So obviously, that's one possibility, right? So if you, one possibility is you keep differentiating, and the left column eventually hits 0. Once you see that 0, you stop the table, cut it off, stop, everybody. Okay, now we plug into this formula. So that's one situation. The second situation is if to deal with that case that we saw earlier where we saw the original integral appear again later on when we were doing that e to the x sine x integral, that's also a possibility. So if you see that sort of thing happening again, you should also stop, because at that point you should be like treating that as an algebra equation. So this means a row appears that is a multiple of the original integral. So you'll see the original integral appear in a row, but there might be a constant factor in front of it. Ignore the constant factor. We know we can factor those guys out. But the moment you see so if you started out with an e to the x sine x, the moment you see a row that looks like some constant times e to the x sine x, you stop the table. That's another possibility. There's a third possibility. It's really when the moment you see a row, because ultimately this table ends here where we multiply across, and ultimately we're going to have to integrate that guy. So another possibility, if it's not one of these two, is you're going to stop when you realize that, oh, this row is easy for me to integrate without integration by parts. It's like we're now hit a situation where we're in a basic rule or something. Right, so you have a row whose product is easy to integrate. Okay, and under this, under these three cases, that will cover every case that an integration by parts can work on, right? So you either stop when the left column hits 0, you stop when a row is just a repeat of the original integral, ignoring any constant factors that might show up, right? So for example, if your v column was e to the 2x, right? Then the integral is going to be 1/2 e to the 2x, and the integral again is going to be 1/4 e to the 2x, and then the integral is going to be, right? So you can kind of ignore the 1/2 or the 1/4 is what I'm saying, right? Ignore the multiple, right? But if you just ignore all the multiples and look at the functions, the row is the same as the original, that means you would stop. Another possibility is, oh, I just see that the column is the row across is something that's easy to integrate. So we're actually going to do a few of these so you can see what I mean. So let's go back to this guy.
I have a question.
Yes.
If we need to multiply across f to the n times g sub n, shouldn't we stop before the left row equals 0? Shouldn't we stop when it's a constant expression? Because if we integrate, if we derive a constant, then we're just going to be multiplying by 0 at the end.
No, because there's going to be a point where you have to do the u times the v that would get missing. You're going to see it. You're going to see what I mean when I actually do it. Okay. So here, you have x to the 5th e to the x. So you know this is going to be a repeated integration by parts. So you're like, okay, I'm just going to do it the tabular way. Let's set up a table. So what we're going to do is in the left column, you're going to keep differentiating. Derivative of x to the 5th is 5x to the 4th. Derivative of that is 20x cubed. Derivative of that is 60x squared. Derivative of that is 120x. Derivative of that is 120, and the derivative of that is 0. And at that point, you stop because you hit a 0, right? Now, on the other column, the right column, it's actually always going to be the same thing, right? It's going to be an e to the x, e to the x, e to the x all the way down. Then you're going to do those products. X to the 5th, e to the x, that's going to take a plus sign. This times this is going to take a minus sign. This times this is going to take a plus sign. This times this is going to take a minus sign. This times this is going to take a plus sign. This times this is going to take a minus sign. And that is actually an important component, which is why we couldn't stop at the row before. Right? So this is the final u times v, and then the last row is going to be the v du. So if I didn't do the last row, I'll miss out on the last u times v in the chain.
Wait, can you repeat that again? What does the 120 become? And what does the E?
0, because I'm differentiating. Derivative of 120 is 0. So I'm repeatedly differentiating in the left column, repeatedly integrating in the right column. Then I'm going to do the product along these diagonals. Finally, I'm going to multiply across here, which of course is going to be 0. It's going to end with the integral of 0, which is just going to be a constant, right? So plus c. So now all I do is I just write that out. So it's going to be a plus x to the 5th e to the x minus 5x to the 4th e to the x plus 20x cubed e to the x minus 60x squared e to the x plus 120x e to the x minus 120 e to the x plus I'm going to have the integral of 0 dx, which is just going to be my plus c. And that's actually the answer. So this means the integral of x to the 5th e to the x dx is going to be e to the x times x to the 5th minus 5x to the 4th plus 20x cubed minus 60x squared plus 120x minus 120 plus c. And if you look at that string, hopefully you can appreciate how annoying it would be to actually go through like this process with all the nested parentheses. It's going to be a nightmare, right?
So,
But-
sorry, would you take the answer without the e to the x pulled out, or
Yeah,
like
it's
would
the
that be
same.
acceptable? Okay.
It's the same, yeah. I just didn't want to rewrite e to the x 5 times again. So that's why I did it. Okay. So you can actually do this. So let's actually redo some, because we took a long time to actually explain the method and then apply it. So it might seem to you that it's just a long, difficult road. But now that we know the method, you'll realize that it's actually super quick if you do it this way. So let's actually redo the x cubed one. As someone who's aware of this method. So I see here that this is an x cubed. I know it's going to be, what's with my 3s? I know it's going to be a repeated integration by parts. So immediately I just set up the table. Keep differentiating. X squared, 6x, 6, 0, stop. Integrate the e to the x, integrate the e to the x, integrate the e to the x, integrate the e to the x. So I go all the way there. Then I'm going to multiply this, multiply this, multiply this, multiply this, while changing signs every time. And so that's going to be x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. And you realize that that was the same answer we got last time. Nice, right? So that's called tabular integration. And it's really just a streamlined version of integration by parts that's particularly useful when you're going to end up in a situation where you have to do repeated integration by parts. But it is integration by parts, which means it'll work even in cases where you don't need this. So it'll work even, let's redo, we looked at x squared ln x. Right? Which for this, I would rewrite that as ln x times x squared, right? Because I want the u on the left side. So the derivative of ln x is 1 over x, and the integral of this is x cubed over 3. And notice that this here is an easy integral, because I will just need the power rule. So that's what tells you stop on the first line, right? So this one didn't need a repeated integration by parts, which means you're pretty much going to stop on the first line. So that you can rewrite as, okay, so this is going to be an x cubed over 3 times the ln x minus this integral of 1 over x cubed over 3. Right. So this is kind of a situation where the tabular method was overkill, but it still works, right? So when integration by parts would work on the first try, it's just like a 1 row that you have to compute, and you'd realize, oh, if I just multiply across, that's just a polynomial. That's nothing. That's easy to integrate, right? So that's like, yeah, that's item 3 here, right? You end up with a row that's easy to integrate. So why don't go any further? Technically, you could go further. It wouldn't really help you though, because I see a row here. Oh, if I just multiply across, it's easy to integrate. Just stop. What about the repeated one? E to the x sine x. Right. So according to Liate, I would rewrite it in this order, because I want this to be my u and my dv. So I'll do the table below. Integral of the derivative of sine is negative cosine. The derivative of that is sine. Right. If I keep integrating the e to the x, I realize that I get to a row that if I multiply across, it's just the original. It's another e to the x sine x, right? But here you stop the original. So it turns out I would have this times this with a positive charge, this times this with a negative charge. Actually, I was thinking in integration. That should be a plus. That should be a minus. I didn't know and catch that. And then I would go across here. So this would give me e to the x sine x minus e to the x cosine x plus, well, now it becomes a minus the integral of e to the x sine x. And then I would just move that to the other side. So that means 2 integral e to the x sine x gives me e to the x sine x minus e to the x cosine x. That's what we got originally. Okay, so you can just stop when you see the original. In fact, this is here is a constant times, it's a multiple of the original because of that minus sign. But again, it's a multiple. So we just stop when there's a multiple. Multiple. Let's see, original. Yeah, so essentially, if you're learning integration by parts, you could literally always do the tabular method. It'll get you the answer every time. Just need to know when to terminate the table. Yeah, and you can get through some very annoying integration very quickly, especially if you have to repeat a bunch of times. So, yeah. Personally, I just do regular integration by parts unless I'm in a situation where I see I'm going to have to repeat all the time, and then I would do tabular. But you could literally always do tabular if you want. If you do some practice, you get used to the method, you could like literally always use it. It'll always work. All right. Any other questions before we move on to the next one? Okay, so we're about an hour in. It'll be a nice point to take a break, I think. So can stretch your legs, have a drink of water, maybe look over what we did so far so that, when we get through the other examples, you'll kind of be okay with it. So we're going to pause here. And all right, we're back. Let's get back into it. So now we're going to do ln x dx. Right? It's about time we learn how to integrate ln. Right? We know how to differentiate it. But there was probably a reason that we didn't know how to integrate it, and that's because it's it's probably not the only way, but it's the least convoluted way to deal with it is like integration by parts. So yeah, how would you go about doing this one? Ideas?
I put the u as ln of x and the dv as dx. I'm not sure if that's right though.
Yeah, you can actually do that. I mean, one thing you can think about is that anything is itself times one, which it seems like a cheap trick, but it's actually an ingenious way to think about it, because that one is actually a polynomial. It actually falls under the A category. So 1 dx or dx can actually be one of the parts, right? Which is why, it's one of the reasons why I go through great pains to always include the dx when I'm doing the parts, because it is actually a bona fide part of the part. So yeah, you can actually make a dx out of it. So it turns out, you want to integrate ln x, but you actually don't know the integral of ln x. So you're kind of in a situation where, well, the ln would have to be the part that I differentiate, right? Like what else am I going to do with that? I don't even know the integral yet. So yeah, you can actually choose those parts in that way. So here, we'd say u equals ln x. Your dv is actually just the dx, or, if it makes you feel a little better, 1 dx. So your du is just going to be 1 over x. Your v is going to be x. So the integral of ln x is going to be u times v minus the integral of v du, which is actually just the integral of 1 dx. So that's x ln x minus x. And that's it. That's the integral of ln. In fact, from now on, I do want you to consider this a basic rule. So we just know what the integral of ln is now, right? It's a thing we know. I do want you to have that memorized. I mean, I think it was in the basic, let me make sure. No, so it's not there, but for us it will be. So add the integral of ln x dx is equal to x ln x minus x plus c to this list. So it's just something that I expect you to know now. I don't expect you to have to derive this all the time from like integration by parts. From now on, we just know this is the integral of ln x, x ln x minus x plus b. Shows up relatively often enough to actually know that. So yeah, that's how I integrate ln. So this also shows you a kind of sneaky trick with integration by parts, is that you can kind of create a part out of thin air by just thinking of the other factor as 1. And then that factor would automatically be an a. And so that will tell you how to actually choose the parts. Yeah, that's the integral of ln x. What we do for sine inverse? We know the derivative of sine inverse, which is, 1 over the radical of 1 minus x squared. You know that as of yesterday, the latest. And so now we want to find the integral of sine inverse. What do we do here?
We use sine negative 1x as the u, and the du is just dx.
So, okay, so we're trying to do a similar thing here, right? So sine inverse of x times 1 dx. This obviously is an a. This is what? An I, right? So who is the u? Shouldn't include the dx as part of that. So according to Liate, who gets to be the u?
The I.
Right. So we start out with the u equals the sine inverse, which I think that's what they said, but I don't remember. And the dv is the dx. I think that's what, was it Nadia that said that? I don't know. Okay, so yeah, now the du, we actually know that now. So we have that. And So this means u times v minus the integral of v du. Right, and how do we do this integral?
I did a u sub with 1 minus x squared.
Okay, can do a u sub with 1 minus x squared. You could even do something a little bit nicer. So here, and again, this actually showcases a very important point that yes, I know we're doing integration by parts, but sometimes other techniques can be involved. There are times when you need several techniques to deal with one integral. So here we're using integration by parts, but while we're doing that, we need a substitution. So this is why it's important every time you see an integral to go through that process in your head about the steps you want to take, right? So you always think basic rule, can I simplify the basic rule? Can a substitution work? Because you don't want to be stuck in integration by parts mode because it's not really going to help you with this integral right here, right? It's actually something that you need to do a substitution for. I would do something a little bit nicer and do like a u squared substitution. That would be nice, right? Or you can think of it as a u equals the radical of 1 minus x squared. So differentiate that 2u du is equal to minus 2x dx. Or in other words, minus u du is the x dx. So the integral of x over this is just minus the integral of u over, well, u. So that's just minus the integral of 1 du, which is u plus c, but the u is the square root of 1 minus x squared. And so ultimately, the integral of sine inverse of x is x sine inverse of x minus the radical of 1 minus x squared plus c. Now,
Sorry, did you lose a negative over there from the negative integral of 1 du?
oh yes, so that's going to be a plus. Because this, I have a negative here, which when I plug in, I get a plus. Compared to, just to show the traditional substitution of u equals 1 minus x squared, means your du would be minus 2x dx, which means minus 1/2 du is your x dx. And so the integral will look like minus 1/2 the integral of 1 over rad u, which isn't terrible. I mean, integrating 1 is nicer, but you can still do this. So this is minus 1/2 the integral of u to the minus 1/2. And so you add 1 to the power, divide by the new power, which means multiplying by 2. So it's minus u to the 1/2 plus c, which we know is minus the radical of 1 minus x squared plus c. So this is something with substitution, which doesn't get talked about in Calc 1 very often. Like the substitution doesn't always have to be u. You can actually tweak your substitution to make the computations even easier. So if there's like a radical, if your u is under a radical, you can make it a u squared instead, so that you don't have to deal with radicals. Right? If it was under a cube root, you can make a u cubed substitution, right? And things of that sort. In fact, we're going to learn something called trig substitution, which shows you that substitutions can be generalized to make your life easier. So sometimes when I see a radical and I make what's under the radical a u, I just do a u squared instead. It can actually greatly simplify the computations. Like here, I'm integrating 1 as opposed to 1 over radical u. Here, it's not a super big deal, but there are times when it can be very annoying. Let me actually close this window here. Either way you end up here, that's going to be your integral. So it's x sine inverse of x plus the radical of 1 minus x squared. Now this is a very interesting one. Did anyone get to solve this?
I did it by parts on the u sub. So after doing a u sub with rad x.
Okay, so you did a substitution with radical x, right?
Yeah.
So this is another thing that doesn't get talked about in Calc 1 very often, because students get into this mode that they think that substitution would only work if you can see the du right there beside it. So they would know, oh, the derivative of rad x is 1 over rad x. So I'll have to see a 1 over rad x somewhere in order to even think substitution, but that is not true. Substitution can work in some cases where it's not blindingly obvious at face value that it can work, which is why it's always step 3. You always think substitution. What would I be able to substitute and how would I get it to work? So you actually can start out with a substitution here, but it turns out you'll end up in a situation where an integration by parts would be the next obvious thing to do. So because there's a u in integration by parts, I'm not going to do a u substitution. I'm going to use another variable. Let's use like a t or something. So substitution. Set t equals rad x. In other words, that means t squared is equal to x. So I can differentiate 2t dt is equal to dx. And so I'm going to plug into this guy. So where I see dx, I'm going to put 2 times t dt. And what else am I going to have left? Well, I'm going to have the e to the radical x, but radical x is t. So essentially now I have the integral of t times e to the t dt, which essentially is just like x e to the x, which we did an example of that before. So here is where I'm going to think by parts, because I have the polynomial times the exponential. So u equals t, my dv equals e to the t dt, du equals dt, v equals e to the t. So this gives us u times v minus the integral of v du. That's just t e to the t minus e to the t plus c. But my t is actually radical x. And that's your answer. So this is one of those ones where it's not really obvious what to do at first, like e to the radical x. What am I going to do with that? Turns out the trick is to first start with a substitution. It puts you in a situation where you're like, oh, by parts can work now in a very nice way. And I use a variable, a t because I don't want to mix up the u's in my substitution with the u's in the by parts. Kind of weird doing that. But yeah, that's how to do that one. It's also worth mentioning here that if you try to jump into by parts directly, which you could do, it'll kind of be weird. And I think you'd end up having to do a substitution to rewrite it in the first place. Like if you did, yeah, it wouldn't really work out. Because you wouldn't know how to, if you think of one of the parts as 1, right, which is an A, that would be the U. Yeah, I don't think it would be very nice jumping directly into integration by parts here, even though it'll take a lot of algebra gymnastics to actually bring it to something that makes sense, where you're like, oh, I see where this is going. But if you start with a substitution, you can see where it's going pretty quickly. That's why the steps are important. Right? Before you think integration by parts, think substitution. Even if it's not obvious that a substitution would work, you never know. You tweak things, you rewrite things. The substitution can still put you in a better position so that other things are more obvious. Right? What about this one?
You could do something similar, and you will get
Yeah,
when you-
what's
when you
your
solve for-
substitution?
yeah. So I did an n sub, n equals x squared,
Yeah,
and then you get a 2x, which cancels out x cubed, that turns into x squared, and then you can turn that also into your sub variable, and then perform an easy integration by parts.
yeah. So if you do that, you realize that the x cubed is like an x squared times an x times an e to the x, right? So you know that this part here, the x dx, that is like your 1/2 dt. And the x squared that's left over here, that is your t. And then you have that the x squared here is also a t. So this guy actually simplifies into 1/2 integral of t e to the t once again. Except here now your t is an x squared, but that looks like something you can do with integration by parts. Which at this point, I think we kind of have the answer memorized. We've done it so often. But here your t is actually an x squared. Another reason why you might want to do that is because, probably this came up in Calc 1 also, is because you realize that there are some very simple looking functions where you can't integrate them. So that would be one of the things that kind of hint to you that integration can be a lot more complicated than differentiation. So for example, we know that, note, The integral of e to the x squared dx is impossible, right? I don't mean it's hard to figure out what it is. I mean, it's literally impossible for us to find an antiderivative for this function. There is no function that we can write down in terms of all the functions that we know, where if we differentiated that function, we would get an e to the x squared. This is an impossible integral. So the fact that I see this guy show up in an integral, I'm like, I don't like the e to the x squared. Having an x squared in the power of an exponential is bad news for an integration, which is what hints to me that I probably want to use a substitution to get rid of that, right? I don't want like a squared variable in the power of an exponential. I'd rather just a linear variable in the power of an exponential, because when it comes to integration, one of those things is death, right? So that's what makes me think, well, I know I'm automatically thinking substitution before I think anything fancy. But once I think substitution, now I have to make a choice. Well, what do I substitute? The x squared would be the obvious substitute in this case, because the e to the x squared is going to be trouble if you don't get it under control. So this is what suggested the initial substitution of t equals x squared. So if you're like wondering why would we start there, and why would we, right? Why, if we're going to start with a substitution, why didn't we pick the x cubed instead, or why didn't we pick something else instead? This is kind of why. At the end of the day, a substitution is supposed to make your integrand look easier, and an e to a linear term is a lot easier than an e to a quadratic term, because one of them is impossible to integrate.
Would it be possible to use the like table method you were using before on that?
Yeah, but but technically you would apply it at this point. Right, the table method replaces the integration by parts. So you could, so it's when you get to this point that you could do the table method. So derivative of t is 1, derivative of 1 is 0, so we stop, integrate this, t times e to the t with a plus charge, 1 times e to the t with a minus charge. That gives you t e to the t minus e to the t. And so that's what this would come from.
Cool, thank you.
Yeah. So the tabular method replaces the integration by parts. It won't replace the substitution portion. What about this one? What is the u and dv here? What are the parts? Ideas? Yes, so anyone have a suggestion?
I haven't thought this all the way through, so I'm not sure if it works, but would you have to do a U substitution or T, I guess, with the T equaling X to the X cubed?
Okay, your T equals X cubed. Your dt would be 3x squared dx. This would mean that you have 1/3 dt equals x squared dx. So that means your original integral becomes 1/3 the integral of e to the t. Well, that's just e to the t. Yeah, it's just a regular substitution. Trick question. Trick in the sense that we didn't need integration by parts at all, but I want to keep you guys on your toes. You always think substitution first, right? Don't work harder than you have to. So yeah, if you just followed the strategy, it's a substitution integral, right? U equals the x cubed, because e to the x cubed is impossible to integrate. So you would suggest you want to substitute x cubed for the power. Then you realize after doing that, you don't need anything fancy afterwards. You end up with a basic rule. What about this one? It would suggest that that by itself is another. Wait, is that one impossible? Probably not, but it definitely looks annoying. So I would say rather than having the square root of an angle, it's much nicer to have just the angle. So t equals square root of x substitution. Right. So whenever you have a weird angle or like a weird thing in the power of an exponential or something like that, and you know you should be thinking about substitution, that's actually a great candidate for the substitution, provided you can get it to work out. So I'd probably start with that. So something like a t equals radical x. So I would plug that in. I call this I. So radical x is just t. And I have my cosine of t. And then my dx is 2t dt. So this here is your dx. This here is your rad x. This here is also your rad x. So this integral just becomes the integral of 2t squared cosine t dt. Now that one is an integral candidate for integration by parts. I also realized that I'd have to do this repeatedly, so I'd probably do the tabular method. Differentiate the 2t squared, I get 4t. Differentiate that, I get 4. Differentiate that, I get 0. Stop at 0. Integral of cosine is sine. Integral of that is minus cosine. Integral of that is minus sine. So I stop there. This times this with a plus charge. This times this with a minus charge. This times this with a plus charge. Of course, this times this would give us a 0, so I can actually ignore that part. That's going to become the plus c. So this would be equal to 2t squared sine t plus 4t cosine t minus 4 sine t. And that would be the by parts. So t squared is just an x, right? So yeah, this is 2x sine rad x plus 4 rad x cosine rad x minus 4 sine rad x. And we have that. So I see that the radix angle kind of freaks me out a little bit. Go into a substitution, get rid of it. I realize then I get just a quadratic times a cosine. The quadratic is going to be an a, the cosine is going to be a t. Integration by parts then tells me you pick the u to be the t part, the quadratic. Keep differentiating, keep integrating. I do tabular because I know I'd have to need at least 2 integration by parts to get through this. So that gets me there. Okay, so we have x cubed sine of x squared. Again, this is kind of weird. So I probably want to do a substitution first. T equals x squared. dt would be 2x dx. So 1/2 dt is going to be my x dx. So this guy is actually the integral of x squared times x times sine of x squared dx. So the x dx, this part is going to be 1/2 dt. This part is going to be t. That part is going to be t. So I end up with 1/2 times the integral of t sine t dt. And here I can do by parts. U equals t, dv equals sine, du equals dt. Integral of sine is negative cosine. So this is 1/2 u times v minus comes plus the integral of v du. And the t was x squared. So it's minus x squared cosine x squared plus the integral of cosine is just sine. We have that. So that's what that one would look like. do want to make a note here because it's actually a common thing for students to mix up notational note. If I write something like cosine x squared, I mean cosine of the angle squared. Whereas if I write something like cosine squared x, that is like the cosine self is squared. So just so you know. Moving on. What's the integral of tan inverse? Well, I mean, we've seen a guy like this before. You see this one function, you don't know how to integrate, but you do know how to differentiate. We do remember the derivative of tan inverse. That kind of suggests that, you know, you just think of the other factor as one. So that's going to be an A. This is going to be an I. Liate tells us the I gets to be the U. U equals tan inverse dv equals 1 dx. So of course your v is going to be x. What is your du? What is the derivative of tangent inverse?
Is it 1 over 1 plus x to the second power?
1 over 1 plus x squared. All right, so now it's u times v minus the integral of v du. How do we do this integral?
Is it just going to be like x plus, I mean, 1 plus x to the second power plus c?
No. That integral, the integral of x divided by 1 plus x squared. Okay, so what do we do when we are faced with this random integral? What is the first thing we think about? Think, is it a basic rule? And it's not, right? That's not in our table. Can we simplify this to look like a basic rule? Not really, with like 2 terms in the denominator. Like the algebra is going to be crazy. It's also like a sum of squares in the denominator. So it's not like you can factor and like try to cancel something. Next thing would be substitution. Would a substitution work here? Yes, no, maybe so. Like if I force you to try to use a substitution, what would you substitute? Just to see if it would work.
One plus x squared.
1 plus x squared. Right, because your du would be like a 2x dx, and you have an x dx there. So this does become 1/2 1 over u du. It's just 1/2 ln of the value u plus c. And so this whole thing just becomes x tan inverse of x minus 1/2 ln of 1 plus x squared. So it's a substitution. U equals the denominator. The du gets rid of the numerator. You end up with 1 over u, which is a basic rule. So that is the integral of the arc tangent. The last one looks crazy. The craziest one for last. All right, how do we do example n? I think this is the last example. Yeah.
I vote that we start by taking care of e to the 2x
Okay, how?
by doing a substitution for 2x.
Okay. So if your u equals 2x, then all the other x's in there are going to become u over 2, and then there's going to be a half on the outside, right? Right? If u equals 2x, then your x would be u over 2. And the du would be an x. The du would be a 2, so you divide that out, you get a half. So essentially you would get something that looks very similar. But at least your x would have like, your e would have like a u in the power. It's easier than that, my grasshoppers. Wax on, wax off. What is the first thing we try to think? It's obviously not a basic rule, right? But you should think it like, okay, is it a basic rule? Nah. Second question, can I simplify this so that it looks like a basic rule? What do you guys think? Can we simplify this?
Maybe split up the numerator and divide each part by x squared.
Yeah. What would you get?
So it would be e to the 2x plus 1 over x plus 1 over x squared.
No, those are basic rules, right? That's 1/2 e to the 2x plus ln x minus 1 over x. Yeah, so what's step 2? So again, just to reiterate, like integrals can look crazy and not be crazy. And integrals can look not crazy and end up crazy. So again, you always do that strategy because you never know what's going to work. Right? You always think basic rule. Can I simplify it to look like a basic rule? And if there's one term in a denominator, that's kind of asking to be simplified somehow. Just try to divide that one term into everybody. See if you can actually get something nicer. But yeah, if I just divide the x squared into everybody, like each term now becomes something that's easy to deal with. And that ends this section. So that's all I wanted to teach you about integration by parts, right? I mean, there's nothing really to teach you about integration by parts. It's all just using that same formula, but I want you to be able to use it in various situations. We also learned about tabular integration, which again is just integration by parts, but it's more streamlined and algorithmic, and it can really save you from doing a lot of work if you're in the situation with repeated integration by parts. And we also saw just because you know about integration by parts doesn't mean things like substitution is now worthless. No, you still need substitution. You still need everything else. And we also learned in the hard way that, yeah, try to use the easy things first before jumping into more complicated, sophisticated things, right? So try to see, is it a basic rule first, or can I simplify it to look like a basic rule before you even think substitution or anything else? Substitution will be what you think after that point. And then if substitution doesn't work, after that point, you start thinking about other things like integration by parts or all these other things I'm going to teach you. So yeah, we are going to pause for a break here. Does seem like we're slowing down. Yeah, 3 hours is a long time to be in a math class, so I understand. So we're going to take a break. We're going to take a breather. The beginning of the next section is actually, hopefully, not that complicated. So it's going to be easier to wrap your brain around it than like integration by parts in these weird situations. So we'll pause there, here, and we'll start off with the next section, which is going to be trig integrals and trig substitution. So we're going to talk about integrating things with trigonometry. So that section kind of starts out with you taking advantage of familiar trig identities. So it shouldn't be too much of a steep learning curve. But then when we get to trig substitution, which we'll probably do in Monday's lecture, then things get kind of tricky, and we'll get through it though. So we'll pause right now. We'll start again. I'll give you guys 6 minutes. We'll start again at 8:10, and yeah, let's take a breather. Get up, stretch, have a drink of water, get up from your desk, move around a little bit, wash your face, whatever. I'll see you guys here soon. All right, we're back. Let's try to get through the last leg. I know it's tough, but stick with me. We'll make it. Won't leave you guys behind. All right, so we're going to start trig integrals, which is section 7.2. And the beginning hopefully isn't too tough. It might feel a little tough because I know your brains are tired at this moment, but generally speaking, it's not going to be too tough. Because we are going to, well, the end of this section kind of gets a little tricky, but I don't think we're going to get to that point today. But the first part is going to be okay. So yeah, we're doing section 7.2, just trig integrals. It is what it sounds like. We're going to learn how to integrate different trig functions, okay? So the main idea is to take advantage of trig identities. So one big thing is going to be the Pythagorean identities, for example. So knowing that, you know, cosine squared is 1 minus sine squared, or sine squared is 1 minus cosine squared, or knowing that tangent squared is secant squared minus 1. Things like that come up all the time. Of course, you also should know about how the integrals and derivatives of the different trig functions interplay with each other. So you know the derivative of sine is cosine, the derivative of cosine is minus sine. So you know these basic identities like that. You can actually get through this thing, but we're going to sort of standardize this, right? So I don't want you randomly pulling at identities. Based on the situation you're in, you kind of know what direction to move in when you want to solve one of these integrals. Okay, so we'll jump in with some integrals that will be useful later. So right now, I'm not going to jump into some strategies. I'm just going to give you some examples of some integrals that you should kind of know how to integrate. And you can use these as some like basic rules. In fact, they are basic rules. I'm going to derive some of the basic rules for you. Let's see. Which ones am I going to derive? Yeah, so like rule 12 and rule 14, those are going to be important. Also, I'm going to derive a rule for you here. I'm going to derive something else that's going to be useful in the future. So the first one I want to do is teach you how to integrate something like tangent squared of x, right? Just tan squared, right? This is going to come up later on, so you should know how to deal with it. And the idea here is to just actually use an identity, right? So recall 1 plus tangent squared is secant squared. So that actually means you would just rewrite this as secant squared minus 1. And it turns out you actually know the integral of secant squared because you know the derivative of tangent gives you secant squared. So that's just tan x, and the 1 is the integral of that is x, right? So we actually know that from a basic rule that the integral of secant squared is tangent x. You also know that from a derivative rule, the derivative of tangent is secant squared. So the integral of secant squared must be tangent. And so, yeah, that's how you would integrate. Yeah, that's how you'd integrate tangent squared. Okay. That's it. Right. So there are times when you have this random trig integral and just applying an identity that you know, you rewrite in terms of other trig functions that are easier to deal with, right? Some of that's going to happen all the time. So that is one situation that I want you to know how to deal with. The other situation is I actually want you to know how to just integrate tangent. Okay, which someone did actually do this in class, mentioned how you get it in class, I think on the first day. So I know you guys can kind of know where this is going. It's to actually use, again, an identity. We know that tangent is sine over cosine. And then you kind of think, well, how can I actually take advantage of that? Well, we know that the derivative of cosine is the negative of sine, which kind of says a u sub might work. So you get the negative integral of 1 over u du. So this is minus ln of u plus c. In other words, minus ln cosine x plus c. And that's the integral of tangent. That is in fact a basic rule, I believe. Yeah. Well, in the rules you see it's secant, but that's okay. That's actually the same thing. Because if you have negative ln of cosine, we know by a log rule that multiples can come up and be powers. And so this is just ln of 1 over cosine, which is just ln of secant. So you can all, this is the same as saying the integral of tangent is also ln of secant if you don't like that negative sign in front. This is a basic rule. So this is a basic rule, and that is an equivalent.
So we can just leave it as the one in the white?
Yeah, you can, either one is fine. But I just want to show you that the one in the table isn't wrong. It's just another way of writing it. So yeah, so you have, that's how you integrate tangent. Another one is to integrate the secant function. And that one's kind of weird. Like, I don't know who came up with this, but they noticed that there's this weird thing that you can multiply and divide by that makes this sort of easy. So this is like, you know, pro level. Like if you didn't see that this is something you could do, like, don't blame yourself. Like, I didn't see this when I was, you know, a little Jhevon. So the trick here is to multiply and divide by secant x plus tangent x. So essentially you're multiplying and dividing by 1. And you are like, well, that's kind of a strange thing to multiply by. And then you go and you realize why it was so ingenious, because if you multiply this out, you get secant squared plus secant tangent. And at first you might think that that looks a lot worse, but when you look closely, you realize that, oh, that's actually a great situation to be in, because the derivative of tangent is secant squared, and the derivative of secant is secant tangent, which basically means that the numerator is the derivative of the denominator, which means a u sub can work. So this becomes the integral of 1 over u essentially. And that is ln of absolute value u. So that gives you ln of secant x plus tangent x. That is in fact a basic rule. You'll see it in the table over here. Okay. So that's how you integrate secant. So these guys are going to come in handy, knowing how to integrate secant, knowing how to integrate tangent, knowing how to integrate tangent squared. The integral of tangent and the integral of secant should be considered basic rules. Like, these are things you need to know by heart. Integral of tangent squared, not so much, but it should be something that you know how to deal with. And the trick here is just apply the Pythagorean identity for secant and tangent, and that will actually do get you through it. So like this or this, I would expect you to have memorized eventually. This I also expect you to have memorized. But if you see like a tangent squared on its own, I expect you to kind of know how to deal with it, even though if you don't have the answer memorized. So those are just some things that I want to deal with. Okay, so now in this section, what we deal with several forms of trig. So So the first class of functions that I want you to know how to integrate is if you have a sine to some power times a cosine to some other power. Particularly m and positive integers. Okay. If they take on other constants, you can figure out ways to deal with it, but I'm going to teach you the way to think about them in terms of integers, right? And this is going to teach you some skills that if they're not integers or if they're negative, you can kind of finagle things and try to figure something out. The second class is when you have powers of secant multiplied by powers of tangent. Ditto. And the third type is just functions of sines and cosines, like more generally. And the fourth type is going to be functions of tangents and secants more generally. Your text also deals with the situation of cotangents and cosecants, but we're not going to do that. It turns out that cosecants and cotangents actually behave very similarly to secants and tangents. So if you know how to deal with secants and tangents, in principle, you know how to deal with cosecants and cotangents. So I'm not going to ask you about cosecants and cotangents. I'm only going to ask you about secants and tangents. So once you learn secants and tangents, that's it. Like you don't have to memorize formulas for cosecants and cotangents, right? That's going to be our focus. But that's just a comment here. But these are the four kinds of things we're going to be looking at in this section. How do you integrate things of these types? Okay, and it turns out you're going to use a lot of trig identities. And I'm going to tell you which trig identities would apply in which situation. So let's actually start that. Let me actually make a note of that so you don't end up worrying about something that you don't have to worry about. We won't cover things like cosecant to the n, cotangent to the n, or integral of functions of this type. I don't know if there are like homework problems that these guys show up in, but at that point, just look up the book for the required formulas. It's going to be very similar to the secants and tangents, except there are going to be a negative signs in annoying places. So it's kind of like we'll ignore, and they will not be on test. They are dealt with similarly to secant, and tangent. Yeah, so don't worry about knowing how to deal with those guys. We're only going to deal with these 4 types, right? We're going to learn how to integrate these 4 types, right? And it turns out in several situations, there's a standard way to approach these types of integrals. And that's what I'm going to teach you in this section, right? So that's kind of a preview. And these guys that I mentioned earlier, they actually come in handy when you're dealing with the secant tangent integrals. Okay, so let's deal with the first one. Okay, so there are subclasses to deal with. Subtypes. So let's deal with A, B, C, D. So here's how we're going to break this down. It's going to depend on whether the constants are odd or even, and that's going to actually determine how you're going to approach it. So we're going to look at the situation where M is odd, N even, or M is even, N is odd. We're going to do M is odd, N is odd, and we're going to do M is even, N is even. Of course, these two here are very similar. And we're going to deal with that later on. Okay, so let's deal with subtype 1. A, integral of sine to an odd power times cosine to an even power. Turns out there's a standard way to actually approach this. And the idea is, here are the steps. And this is generally going to be a standard approach, right? You want to save a factor of the odd power, right? So 1, save a factor of sine x, as in move it to the side. Okay. The second, you're going to change all other signs to cosines. Of course, you're going to be using that identity sine squared equals 1 minus cosine squared. Then you're actually going to do a substitution. U equals cosine. Once you do that U equals cosine substitution, that original sign that you move to the side in step 1 is obviously going to be your du. So that's going to be nice. And then everywhere else, you're going to have cosines. Each of those guys are going to get replaced by u. So at that point, it's going to be easy to integrate. So let's do an example here. Let's say I ask you to integrate sine cubed x times cosine squared x. Okay. So you have an odd power of sine and an even power of cosine. So first thing you're going to do, save a factor of sine. So you're going to go in and you're going to just take one of those factors of sine and you're going to move it off to the side, sine x dx. Okay. The second thing you're going to do is change all signs, change all remaining signs to cosines. Which means here I have that sine squared. I'm going to change it to 1 minus cosine squared. Now we're just going to do the substitution. So you have u equals cosine. Your du is going to be negative sine x dx. So this is going to give you negative the integral. Everywhere you see a cosine, you're going to plug in a u. And your sine x dx is going to be your du. So now you just integrate. At this point, we go through our art of integration. What does this look like? Is it a basic rule? No. Can I simplify it to look like a basic rule? Yes, by expanding. By multiplying out, I get it to look like the power rule. And so now u cubed over 3 minus u to the 5th over 5 plus c, where your u is the cosine. So that's everything. So this is like a standard thing, right? If you have an odd number of factors of sine and an even number of factors of cosine, you always do this. You save one of the signs, you change all remaining signs to cosines using the Pythagorean identity, then do u equals cosine. You'll always just get like a function of u's, which then you just integrate using some integration technique, right? So you get, yes?
In the last step, or in the second to last step, it becomes u5. Why do you go from u to the 4th power to u to the 5th power divided by 5?
Oh, I actually integrated. So that's the integration rule. Right, so that we know that the integral of x to the n is x to the n plus 1 over n plus 1. So you add 1 to the power, divide by the new power. So 4 plus 1 is 5. So it becomes u to the 5 divided by 5. Any other questions? Are we getting the idea here? No, I meant these two. Right. Now the reverse, if you had an odd number of cosines and an even number of sines, it's essentially the same strategy, except the sine and the cosine switches roles, right? So you'd save a factor of the cosine and then use the sine. So that's going to be a very similar strategy. But here's another one where it might not be obvious right away that you should use this strategy, but you should. So an example. What if you end up having to do just the integral of sine cubed? Okay. So it turns out it's the same strategy. And why is that? Because you can think of this as sine cubed times a cosine to the 0, right? Which is 1, and 0 is even. Which tells me that don't really need positive integers here, just integers. Because 0, you should also consider it as it just means that 0 is possible. It just means that one of the trig functions won't be visible. And negative just means this thing moves into the denominator and you have some sort of rational integral to do. So it can work for all integers. So again, you have an even power of cosine, so you do the same strategy. You save a factor of the sine. Change all remaining signs to cosines. Then do a u equals cosine. Your du is going to be the negative sign. And so your integral just becomes the negative of, in this case, 1 minus u squared. Then you apply the power rule. U in this case was cosine. And that's how you'd integrate sine cubed. Are we getting this? Any questions? Anything unclear? All right, so that's pretty much case 1, right? If you have an odd number of sines and even number of cosines, you save a factor of sine, change all the remaining signs to cosines, do a substitution, u equals cosine. For B, when you have the integral of sine to an even power times cosine to an odd power, this is very similar to case A. Just that the sines and cosines switch roles. Okay, so instead of saving a factor of the sine, you're going to save a factor of the cosine. So for example, the integral of, say, sine squared x times cosine to the 5th x. Okay, you have an odd number of cosines, you have an even number of sines, you save a factor of the odd power. Then you're going to change all remaining cosines to sines, right? So you're going to use that, of course, the identity now, you're going to change cosine squared to 1 minus sine squared. So this is going to be 1 minus sine squared, right? Because this guy here is cosine squared squared. And now you're going to do u equals sine. Your du is going to be that cosine. And so you end up with the integral of u squared times 1 minus u squared squared du. And that one you can integrate, right? You go through the steps again. Is this a basic rule? No. Can I simplify this to look like a basic rule? Well, if I just expand the parentheses and multiply out, yes, I would get the power rule. So I'm going to go with step 2 in our art of integration strategy. So that's just going to be u squared times 1 minus 2u squared plus u to the 4th. Right, using that formula that we did in first day of class, a minus b all squared is a squared minus 2ab plus b squared. That's u cubed over 3, 2u to the 5th over 5, plus u to the 7 over 7, using the power rule. U in this case was sine of x, so this is going to be sine cubed x, sine to the 5th x, sine to the 7th x. And so that would be that one. Questions on this one? So the upshot is if one is odd, has an odd power, one has an even power, save a factor of the odd power, change the rest to the other trig function using that Pythagorean identity. Now the question is, what if both are odd? It turns out that you have a choice. You can save a factor of either one and then do the same strategy. But it turns out, computationally speaking, it's better to save one than the other. And the answer is you should save a factor of the smaller one. So let's actually deal with that. So C. So this is the case where I'm integrating sine to an odd power and cosine to the odd power. So they're both have odd powers. Technically, you could save either one and do the above strategy, but it's actually better to go in one direction than the other. So steps here to save a factor of the trig function. And later on, you'll see why with the smaller power. smaller in magnitude. Then you're gonna change the other trig function using sine squared plus cosine squared equals 1. Then 3, substitute u equals the other trig function. For integrate. So let's say I have a sine cubed times cosine to the 5th. Okay, so in the case that both are odd, this is the strategy. Technically, you can save either one, but saving the smaller power will always put you in a situation where it's computationally easier to dig yourself out. So in this case, the sine has the smaller power. So sine x has the smaller power. We'll save a factor of the sine. That's what we're going to do. So here, I would think of this as sine squared times cosine to the 5th times I save one factor, pull it off to the right. So now I'm going to change the sine into cosines. So that's going to be 1 minus cosine squared. Then du equals cosine. My d is going to be negative sine. So this integral is going to be 1 minus u squared times u to the 5th du. I will multiply this out. This is u to the 5th minus u to the 7th. It's going to be u to the 8 over 8 minus u to the 6 over 6. U was cosine. Now note, if we saved a cosine, what would have happened? You would have an integral of sine cubed times cosine to the 4th times a cosine. You would change all the cosines to sines. And then you would do a u equals a sine. D would be the cosine. And you would end up with u cubed 1 minus u squared to the squared du. And that is a little more annoying than this. obviously, because here you're going to have to expand the quadratic, then expand the second set of parentheses. So if you save one of the bigger powers, you have to contend with a higher power remaining after the substitution. And that just makes, you'd have to expand a binomial with a higher power in the end. So that just kind of makes it a lot harder. So saving a factor of the smaller power works. So I'll introduce what to do in the last case, case D, and I'll leave the examples for you guys to try. So D, what if they're both even? So have sine to an even power and cosine to an even power. So there's no odd thing to factor out one and save one of them. What do you do? The steps for this such a case is one. Oh, my headphones are dead. Is you apply the double angle formulas. So these are the ones that tell you that sine squared are here. Put these away.
Can you guys hear me? Okay. So sine squared, you actually know it's 1/2 of 1 minus cosine 2x. That was something you probably learned in trig. It's been probably a while ago. This is 1/2 1 plus cosine 2x. So these are two formulas that I do expect you to remember. Afterwards, to simplify and apply methods in the previous cases. Okay. So I would say try these. Should I number them? Integrate cosine squared. Integrate sine squared. Integrate cosine squared times sine squared. Integrate sine to the 4th cosine squared. Okay, yeah, try those 4 for next time. And we'll stop there. So this deals with even my iPad is spazzing out. It's like, we're going too long. Can't do it, Captain. Okay, so we've covered case one pretty much. So we did this for sines and cosines. I'm gonna move on to case three next time, and then we're gonna deal with secants and tangents. But in this last case, I'll leave that for you to try. And we'll pick up with those next time on Monday. But yeah, that's all I wanted to do today. Any questions before we go? Right, so you guys know where to find the notes. So if you missed anything, you have it, and I'll have the video up for this pretty soon, because I've the Zoom changed a little bit, but I figured out where the setting is that I need to switch now. So the video should not need a lot of editing. So it should be up very soon. That being said, we'll say good night. It's been a long night. Integration by parts and tabular method, of course, can be a little complicated to get it through your heads, but don't worry. Keep studying, study over the weekend. Next week, things should be clearer. So for that, I would say good night. Have a good one, and I'll see you guys in the next one. Ciao.